Hey everyone who joined and who listening this recording. Today we have on our AI and blockchain security workshop a Fuzzland team. So they will present their advanced fuzzing tools and tell more about LLMs and AI for cybersecurity in Web3. Here also with me, Carl, our security researcher in our community. So yeah, let's just start. Um, yeah, you can share and you can speak.
Hi. Hi, everyone. Um, my name is Key. My handle is public key, as you see on my screen. You can reach me out on Twitter or Telegram or Discord if you have any question about this presentation. So today I'm going to talk about fuzzing and how AI can be integrated into fuzzing, or more generally, security research. So first, let's talk about fuzzing. So what is fuzzing? So this is a punch card in 1950s when programmers use this card as a program input. They put this card into a big weird machine in a room, and then they test the robustness of a program. Sometimes engineers just pick up from the trash bin those discarded cards. They use it to test the robustness, and maybe sometimes they find some bugs. So the concept of fuzzing, the word of fuzzing actually appeared in 1980s, but the behavior of fuzzing actually started way before that. And fuzzing is really execution. It's a type of program analysis. On the right, we can see there are different types of program analysis, and program analysis is really helps or it helps human or a machine to understand the program. And program analysis is really a hard problem. As a matter of fact, it's an MP hard problem. You cannot analyze all types of programs and in polynomial time. And so we have some trade-offs. You can see on the there's a graph on the right. We have some static analysis on the right, on the left, and some dynamic analysis on the right. And also, there are 4 quadrants, and on the y-axis, it's automatic versus manual. And let's talk about some most commonly seen analysis methods. So the first one is static analysis. It's very manual. Sorry, it's not. It's kind of in the between of automatic and manual, but it's very static. It's the most static thing. So some examples of static analysis is compilers. Like when you're writing a program, your compiler will do a static analysis. Let's say do some optimizations, eliminate that code, or even I guess the most basic thing a compiler does is to check your syntax errors, right? Otherwise, it cannot compile. It will convert your source code into, say, AST, and then compile it into machine code. And also linters, if you write very bad indented code, linters will help you to do that. Or if you use some unused variables, compilers or linters will do that. And also, there are some checks of overflows. That really depends on the tools a static analysis tool can do. And yeah, there's tons of examples here. And some pros and cons for static analysis. First, it can be very precise. For example, the example of overflow. If you implement some overflow detector in your static analysis tool, it can be really precise. And it's really fast because you basically write those rules before everything. And these rules are, it can be executed really fast. It does not need very much computation. And some cons, it's slow in some sense. Let's say if you want milliseconds of reaction time, it can be slow. It takes maybe a few seconds, but it's a relative slow. And there are some false positives. Well, this is also understandable because sometimes we want all the positives, even some are false positives. For example, if you use some static analysis tools for smart contracts, you'll see a lot of false positives. But I mean, those are for human to like filter out those false positives. And next is formal verification, because this is also a hot topic in smart contract security. So formal verification, you can think it of like a math proof. Basically, it's converting your smart contract into a math formula, and some properties or invariants in this math formula can be proved to be true. And also pros and cons. So the pros is mathematically rigorous. So if it's proved to be true, it stays true forever. And this is very like crucial for a smart contract to meet some invariants. And also it's exhaustive, meaning that there are no chance of being wrong. Like all the possibilities are considered in a formal verification. And for the cons, first, and maybe I guess it's one of the biggest ones, is poor automation. Like you have to be very experienced in formal verification to write those formulas. And really, if you're trying to use some automation tool, it may not work that good. And also scalability is a problem. Like you cannot. It's similar to automation. Like you cannot write one tool to adapt all contracts. You have to like make the proofs case by case. And the last one is it's really slow. It takes not seconds, but tens of seconds to sometimes complete a proof. And that's already a fast time. Sometimes it takes minutes or sometimes hours. That's also possible. And it takes a lot of computer resources. Next is symbolic execution. You can see it up here. It's automatic. It's somewhat static and somewhat dynamic. So I will dive into this topic later. So I will just quick go through the pros and cons. So the pros is it's precise. So by precise, it means that if you find a bug using symbolic execution, it is there. It gives you a precise input to trigger the bug. And some cons, it's a little bit slow because it's like using symbolic values as execution as you execute. It's kind of like solving an equation, but not like globally solving the equation like formal verification does. It's like solving one path of the program. But anyways, I will dive into this later in this talk, so I just skip here. Another problem here is path explosion. And this is the biggest problem in symbolic execution. Basically, symbolic execution, like I said before, you execute with symbolic values. So when you reach a branch, let's say if you reach a if branch, it will split into two paths. So the program will like exponentially increase its complexity to store the states of the program. So this is called a path explosion. Let's say if you have a for loop, so it's going to be one for loop usually will explode your symbolic execution engine. And the last one is fuzzing. Fuzzing, like I said before, it's execution, like concrete execution. You throw a random input, well, not that random, but like comparably random input into the execution engine. In our example, maybe a EVM executor, and we just let it execute. So because it's a concrete value, so we do not like observe what it does or use symbolic values. So it's gonna be fast. And the cons, it's not exhaustive because, well, you cannot like iterate over all the possible inputs. So sometimes, or a lot of times, you cannot reach all the branches. Well, reaching a high coverage is our goal, but after all, it's not exhaustive. And another cons is when meeting complex conditions. Like say, if you are doing a comparison to a message sender, it's an address of 265 bits. So like throwing a random input into it will or may not likely to find an answer for that fuzzing case. Okay, so that's for the program analysis. And let's dive into fuzzers more. So how a fuzzer works. This is a diagram of a very simple fuzzer. So it has four stages. So the first one is initialize. It's like setting up all the environments you need. Maybe let's take an example of a EVM machine. It's like maybe if we are using get, we need to set up a genesis.json, right? And also we need to like set the contract code, deploy the contract on the EVM machine you had there. And then after initialization, we generate input. Generate input is like in the previous slides, I said random, but really like random sometimes means nothing, right? Like if you have a well-defined Solidity contract code, throwing random data into it may not, or even touch some function selector. So generate input, oftentimes we use the abi.json file or the ABI definition of the smart contract to generate an input. And for the parameters of the inputs, sometimes it's random, sometimes it's carefully crafted, sometimes it's formatted. Then after the generation of the input, we execute this program with our input. And this is not much to do with our fuzzy implementation. Sometimes we just, or oftentimes we just used pre-implemented EVM machines. Like in our fuzzer, we used REVM, which is a Rust EVM. It's very fast. And then we evaluate the result. So this part is, it also has like different algorithms for evaluation. Like how do you define some output is, or some state, result state is interesting or not? Maybe you steal someone's money for using like nothing. That might be an interesting state. And also maybe you reach some very rarely reached branches. That can also be an interesting state. And after evaluation, we either find a bug or we use this evaluated data to help our input generation in the next iteration. So this is really a huge while loop. And yeah, like I said before, the two important components of this fuzzer is input generation and evaluation. And let's look at some examples. Okay, so this is an example of evaluation. So this is coverage guided fuzzing, and it is like still, I guess, one of the most popular one, at least in Web2 space. So let's look at this graph. It's a composition of a fuzzer. So first, we have a seed pool here. A seed pool is some initial corpuses or inputs. Maybe it's sometimes we just scrap it from previous transactions or in Web2 space previous like files. Well, let's use an example of a PDF reader. Maybe we can scrap the internet to get tons of PDF example files, and we put it into the seed pool, and then we randomly select a seed or select a file from the seed pool. When we get this seed, we do a mutation. A mutation is, as it says, mutate the input. Sometimes it's like say a byte flip or a bit flip, or sometimes add some bytes, yeah, something like that. And then we have this input. After that, we feed this input to the target program. In the example of a PDF reader or an image reader, it's a parser that parses binary data into some meaningful structs. And then we either find a bug. In this case, a bug might be some crash, or we reach some code. So this code, it's programming counter. So each time we input a new input into the target program, it may or may not reach some new branches. If it reach new branches, we might consider it as a interesting input, and that's why this coverage is it's like the heuristic algorithm for this evaluation. And if some inputs reaches some new program counters or new branches, we will tell the fuzzer that this input is interesting, and we will add this input into the seed pool. And this is, again, a huge while loop. And this is how the very simple coverage guided fuzzer works. And this is fuzzing in web. Sorry, let me change it. Fuzzing web 2. This is an example of fuzzing in web 2, a stateless fuzzing. I will explain what stateless and stateful in these two slides. So let's look at the C code on the left. So we have a parse data function. This can be a external function, like implemented by someone else, or some function you want to test. And then we have this main, main function where you have an input of some buffer here, and inside this while loop, we just read standard input and the length. This is like the fuzzer will feed the input into the program, and it will be put into the input char array. And then we call this function, it's parse data. And then this can be generalized to varied applications in Web 2 space. For example, a PDF or image reader, or a HTML renderer. Let's say if you write a raw HTML file and you throw it into a renderer that renders the page for you. Sometimes it can be a JavaScript engine, so it's a program execution engine. And one key thing here is that it's stateless. What do I mean by stateless? So each time you call parse data acts the same. It does not rely on anything else other than data itself. So this is very common, right? So in the examples here, it's very reasonable that we have this stateless fuzzing. But in Web 2 space, Web 3 space, let's see how the contract would look like. So this is a very simple contract foo. We have a parse function. It takes one parameter of int a, and after some parsing logic or some business logic, it will reach this line. If a is greater than hex 1337, it will trigger a bug. And for human, it's really easy to see because this is a simple contract, so it's easy for us to see how to trigger the bug. And for a fuzzer, also it's very easy for it to discover the bug, because all it needs to do is call parse on different a's. Like for a, you have 2 to the 256 possibilities, and sometimes maybe a 0, because sometimes a 0 can trigger the bug. And sorry, a non-zero, something bigger than hex 1337 will trigger the bug. That's a high possibility. But no one writes code in Solidity or in Ethereum or even in blockchain like that, because we want to keep things. One key feature of blockchain is to store things, right? So more likely, we have a storage variable inside the contract. It's a int s, and we have two functions. So one is hack. Hack does some logic up there, and then it says s to hex 138, and pawn will check the value of s and trigger a bug, depends on the value of s. And this is like a analogy of some other contract, maybe I guess all contracts that uses a storage variable and has a bug. Yeah, and one key thing to realize here is that you have to make two function calls to trigger the bug. So first you have to call hack, update the storage variable, update the state of the EVM, and then you have to call pawn to trigger the bug. So what we really need here is that for stateful fuzzing, we need fuzzer input not just being the input data for a EVM, but we need to keep the state of the EVM. So a fuzzer input in the stateful fuzzer is EVM input plus the state of the EVM. And back to the example we talked before for stateless fuzzing, I said it's useless, right? It is useless in my opinion. And stateful fuzzing is our the goal we want to achieve. And sometimes I think people are like confusing the concept of fuzzing. I feel like fuzzing is stateful fuzzing is fuzzing, and also invariant testing it's similar to stateful fuzzing, and sometimes they are equivalent. Yeah. And let's go back to the diagram mentioned above. So we have input generation and we have evaluation, and what more should be added to this simple fuzzer. And here I present to you our open source project. It's ETFuzz. You may have heard it before, and it's stateful fuzzing. And also we are adding some new features, which I will talk about in later slides, and to make this fuzzer more smart than rather than random data. Okay, so the first let's look at the architecture of this fuzzer. This is like a screenshot from our paper. So first, these parts circled by the red square is it corresponds to the fuzzer the input generation in the previous slide. So we have a seed pool. A seed pool you can see here. It's composed of corpus. A corpus is just a seed mentioned in the previous slide. And a corpus is consisted of a state and a transaction. So yeah, that I explained before why we need to keep the state of the fuzzer or the EVM. And then after choosing one corpus from the corpus pool, we mutate it. Sometimes it's just some simple mutation like byte flip or bit flip. And sometimes we use some ABI-based mutation, like we do not simply do the flips, because sometimes very oftentimes it's useless. So we do some smart mutation, and then we get this input. After getting this input, we are reaching this EVM executor. Like I said before, we are using our EVM, Rust EVM, as our EVM execution engine, but that's just that's one part of our executor. And another feature of our fuzzer is concolic execution. So before concolic execution, let's talk about symbolic execution, because concolic is like it's concrete plus symbolic. So let's look at this code first. This is a C code. It's a very simple one. So the source code is here. It's a function f. You take two parameters. One is x, one is y, and then you compute some variable z, and then you have two branches. First is you check the value of x, and then you check the value of if the value of x is smaller than z, and if it is, it will assert 0, which will trigger a bug here. So let's look at how this source code will be converted into a CFG or control flow graph. This is, after its compilation, it will be translated into machine code, right? And the machine code can consist of the blocks. A block is a consecutive sequence of instructions, and this is a diagram for that. So we have two branches. So if so the first if will check the value of x if it's equal to 100,000. If it is not, it will not do anything. And if it is, it will reach the second comparison. If x is smaller than z, it will trigger the bug here. But the value here is like ignore the values here for now. And then if it's greater than z, it will reach this block. And after this like execution, because we are having x as a symbolic value, so at this point x does until it reaches the exit, x will not be solved by the solver. So we are really having 3 branches here. That's how symbolic execution works. When it reaches the exit of the program, it will the solver sometimes or many times it's a SMT solver. It's like it will solve think it of a black box that will solve all your equations. And when it reaches the end of a branch, it will do the solve and give a concrete value of the program input. That's why I said before why symbolic execution is precise, because for each branch, the solver will ultimately give you an input that reach this program counter. But it raises a question, I said before, about path explosion. Let's look at this function. This is again a function of f, and it will take one parameter of x, and a stack variable I is 0, while x is not 0, x will self-decrement, I will self-increment. If I is hex 1 through 37, a bug is triggered. For us humans, it's very easy to spot the bug, right? As long as you input x is equal to hex 1 through 37, the bug will be triggered. But let's think it as if you are a symbolic execution. Each time you reach a x is not equal to 0, you will split out 2 branches, right? So after this execution, you will have 2 to the 2 to the thousands of branches, which will explode your memory. That's why we call it path explosion. So this is why symbolic execution may not work very well, like ideally in a program analysis, not even And what we did on top of symbolic execution is that we used concrete execution. Concolic execution. So it's a combination of concrete execution and symbolic execution. What we do is that, let's use this example again. So first we use fuzzer. A fuzzer will, let's say, generate a random input for x. Maybe x is 0 to x is equal to 1, and then it will use the concrete execution engine, in this case our CPU, right, to execute this program. And after that execution, it will only have one path, because we have a concrete value. It will only go one time for the this comparison. It will only branch once. So we, based on this execution trace, we meanwhile we maintain a symbolic state for the execution, and for each branch we have, we only solve once for the concrete value. So basically, it's like symbolic execution, but not entirely symbolic. It's like it only solves one branch aside from the concrete path. And our concolic execution engine can solve simple tasks and like a match sender comparison, or sometimes a transaction origin comparison. And this is very useful for some like hacker controlled contracts. For example, like many contracts owned by hackers, they have a owner comparison, right? And sometimes if we want to use a symbolic execution to analyze the, like, after the owner check is passed, what will this contract do? And this is very helpful for that. And now let's look at the another component we have in eTFS. So besides execution, after execution, we have evaluation, right? So evaluation, we have two cases. If we think the result state is problematic, we will like say it's a bug. If not, we will add the data or add the metadata of this execution trace to the corpus pool, and we have. Oh, okay. So let me explain you about these two components first. So one is execution waypoints, and this is like it's basically the coverage guided part. So execution waypoints is like when you reach some new code block or some new PCs, we will think that this input is interesting because it's like triggering new branches. And we will save this state, the current state and the transaction to the corpus. Next time, we will or we will choose from this corpus seed. And then we have a state waypoints. And this is also a heuristic algorithm we implemented in ETFuzz. So the concept behind this is that if some input triggers some state variable that is important, we might think this input is a important input, and we will add this also. We'll also add this state to the state pool. And by important storage, we sometimes we can customize. Let's say I manually know that this storage variable is important. I don't want it to be some value. We can do that. And secondly, we can if a input touches some storage slots that has never been touched before, we also think this is a interesting input. This is very like straightforward, I think, because yeah, that's like by saying it out, I think it's already very important or interesting input. And last thing is about oracle. So a oracle is like it's a feedback mechanism to decide whether a input or the state after an input is interesting, is a bug or not. And for oracles, we have different types of oracles. The ones I listed a few we implemented so far. These are generic, like they are very general for the types of contracts there. So we have ERC20. Sometimes, like if it's a rug pull token, we can immediately find it if the owner can like rug pull your fund, and this can be this really can be an indicator of the security of a contract or a token. And also arbitrary call is like if some contract can arbitrarily call some address with arbitrarily crafted call data. And also Uniswap V2, this is also a popular app, right? So if a pool can be, we can drain the funds using, let's say, flash loan. Our fuzzer can find it really quick. And also we support Foundry and Enchinda and Scribble invariants. That's the ones you write in Foundry or Enchinda or Scribble. If you have write invariant test before, it's basically emitting a log onto the EVM machine, and we capture that log. And we have other oracles now listed here, but these are the ones I feel very important. And yeah, let's talk about AI. So how can AI help fuzzing or security in general? So I have these are my own opinions, and I think one pros of AI is that it really helps human read unreadable code, and sometimes it can be inside, say, audit. There are thousands of lines, and sometimes it can be really unreadable. Here's an example. So this is a CTF challenge I did before in Curta Cup. So this is a U assemble code. So as a human, I cannot easily see what this code does, right? I guess you cannot as well. And I will ask GPT to explain what the code does, and it will first like format this code for me, and then it does like some explanation, and I ask it to do more to convert into a Solidity or pseudocode. After its like step-by-step explanation, it gives me this. This is more like readable. So first it assigns a mask, and then a result. Result is some variables there, and with some comments there. And lastly, it sets the memory start to some result. Yeah, and this is what I mean by helps human read unreadable code. And we have some like in the house we use GPT to analyze those malicious contracts as well. So sometimes we detect some features of a malicious contract, but usually or for all cases the hackers will not open source their code, right? So we can use GPT to help us to understand the code. And well, before stepping into Web3 security, I used to be a Web2 security researcher. And I have a lot of scenarios like reverse engineering some binaries. Sometimes if it's like C++ or Objective-C, there are going to be a lot of dummy results where you have to like you make your mind to ignore those lines generated by the decompiler. Yeah, but with the aim of AI or with the aim of LLM, we can ask AI to do that for us. And there are still a lot of cons for AI right now. And the very first one is slow token generation. I know it's already faster than like maybe a year ago, but it's still slow, especially for our fuzzing case or some cases you need speed. It's too slow. We cannot like let the AI to say what should the next input of this contract be, and then do fuzzing. It's just way too slow. And the second one is context length. So AI can, so far, I think Web3 is a good test field for the AI because most of the contracts there, they do not have a lot of lines. But in a larger code base, let's say the Linux kernel or some browser source code with millions of code, AI just cannot do it. And another, the last one is it's not reliable. I guess everyone has experienced this before. It will sometimes just constantly apologize for what he said. And then, yeah, you just have to differentiate with human mind, whether it's correct or not. But I think this problem will be like improved soon. I heard that they're training GPT 4.5 or releasing it sometime. Yeah, I guess this will help us in the future. Yeah, and lastly, some examples of using AI in our security research or testing. So first, it can write invariant testing. Like I said before, it reads or understands the contract to some extent, and it can be used help you to write invariant test and also do contract analysis. That's the things we are using AI to do in our company right now. And yeah, that's basically the presentation. Thank you for being here. And I'm open to all questions if you're confused about anything.
Yeah, thank you so much for the presentation. It was awesome. I have my personal question is that um how exactly in Fuzzland the AI is integrated, or how you
Well,
leverage
this
AI in
is
your product?
yeah, this is we have two parts, like I said before. So AI, we are building a AI. This is not released yet. We're building AI to write invariant tests in our service. It's called Blaze.ai, but yeah, AI is the service of it. It's like a service version of ETFuzz. And another thing we're using constantly is do those malicious contract analysis. But this is an in-house tool. Sorry for that.
What do you think about LLM in the compilation and analyzing of exploits? How it can, how LLM can leverage those processes?
Okay, so I can tell you a little bit about how we use LLM to analyze the contract. So first, smart contracts are usually written by Solidity, so it will have function selectors. And we first use decompilers, existing decompilers. For example, Dedub, they have a cool decompiler, online decompiler. And also we have Hamidol, and we use, this is one part, it can, to some extent, recover the source code of the bytecode. And then we have the bytecode. So we feed three sources. One is the online decompiler, and second one is Hamidol. It's a Rust written local decompiler, and lastly the bytecode. And with the so we feed these three into the LLM to ask it to like explain what the contract does, and it really worked pretty good. For example, it can even like recognize some arbitrage contracts, and sometimes we haven't like but for those like huge hacks, for example the Kyber swap, we don't need well, we can use AI to analyze what it does, but our like system already tells this is a really malicious contract. But yeah, AI can, or LLM can do that really well.
If I may ask, well, first of all, thanks for all the deep explanation of fuzzing and so on. I actually see that you guys are experts on this, and actually something that some experts on fuzzing, symbolic execution, formal verification. So I think something that lots of us is trying to do is learn about it, and it would be very convenient or interesting if you can tell us what are your sources for learning. Where have you actually studied deeply symbolic execution so that you get to this level? Maybe you can share some.
Well, that's a good question. I think so for fuzzing, I guess well, it's for me it's pretty smooth transitioning from Web 2 to Web 3 fuzzing, because fuzzing in Web 2 is really popular. It's like the top one bug finding tool. And yeah, I think if fuzzing, as a developer, it might not be that straightforward. But from a security researcher's perspective, fuzzing is it's a method that just comes into your mind when testing things. Yeah, I think it maybe as a developer, unit testing is more of the option, but yeah, I'm not sure about that. For symbolic execution, it's a product of the academia thing. So yeah, again, for me, it's like learn those from from school, and but I guess it's our mission to make the developers to use this tool more smoothly, right?
And have you noticed any material or anywhere, any blog or articles that...
Oh yeah, I think there's a fuzzing book. This is like it's a super good source, but it's like way beyond the need of Web3 fuzzing. But it's really good for you to look at it. Well, in this book, I guess there are some. Let me see. So I guess there's some terminology explanation. For example, what is coverage? When should we stop fuzzing? Something like that. You can check this out.
Okay, and it says things about symbolic execution as well, or that's a separate thing?
For
You say you learn
symbolic
it in
execution, I remember there's a course or a lab in yeah, I will find it and post it in the channel later. I think it was from MIT. Yeah, symbolic. So it's like you have to for symbolic execution. It's really once you understand how code runs on the low level, it's very trivial for you to think about let's solve it with symbolic value. And for that part, we do not care about how you should be how it solve how or the solver engine solves it because it just does it for us. Yeah, I'll post a lab later in this channel.
Okay, and I mean, you've mentioned ETFAS.
Mhm.
I actually was wondering if you can, I don't know, share more things about it, like because you mentioned it's about symbolic execution and fuzzing. I don't know,
Yes.
do you have any maybe examples or any? Because I've been checking your GitHub, and you're actually saying that it is much faster and better than Foundry, than Echidna, and so on. So there are some nice stats there. And if you could just go a bit more about it, just give us some quick overview. Sorry to put you there on the spot, but I'm sure you know it by heart. So
Yeah, sure. So this is our repo. We have some inside this test folder. We have all the tests we support locally, and well, what for the comparison to other fuzzers, I did not like mention it in this slide because I feel like it's a little bit too competitive, I guess. But the thing about our advantage is that we are using the state plus input is our I think it's new in our fuzzer. And for other fuzzers that keeps tracks of a state, they keeps tracks of a series of transactions. That's why that's the reason we're faster because we're only like storing one state and the transaction instead of a series of transactions. So for the series of transactions, you have to execute from the start, which will cause a lot of overhead. But again, yeah, that's also a proper method. But like fuzzers are improving, right? So yeah, that's the benchmarking. And yeah, I think what we are trying to do is to let developers write as less as possible and put it on our side. And maybe I should answer to the question mentioned before.
Yeah, I think Melvillian have a voice right now, so you can ask directly. Yeah.
Groovy. Thank you. And
Oh.
also, thanks for doing the whole presentation. I was really excited to listen to this. I
Mhm.
have a bunch of questions, but
Yeah.
just to answer your first one, you were asking more like, what did I mean by pyrometer? So it seemed like a go-to tool because the way pyrometer works is, remember how you're giving the example of symbolic analysis and you're looking at the if statements and you can kind of prune away just by you like being a human, you can look at it. Obviously, machine can't do that immediately. It needs some intelligence. And so the thing that pyrometer does is it's basically a symbolic like analyzer, but it's specifically made for Solidity or for the EVM, maybe for Solidity. And I don't know, it just seems like one of those new tools that seems purpose built for fuzzing, for pruning the fuzzing and containing the giant state. What did you call it? State bloat or
Yes, the
I forget what you
explosion.
said. State explosion, yeah. But anyway, it sounds like you don't use it, so that's cool.
Yeah, I think yeah, I'll definitely check it out like how they do it. But state path explosion is always a thing. Like they can, I guess they did some efforts like pruning some of the states, but
Right.
this is a very the while loop is a very simple one. So
Yeah.
I think there are cases it cannot reach. But yeah, definitely brilliant work they've done, I guess. But
Who knows?
yeah. I'll check it out. And let's move to your second question. What LLMs you're using? Right now we are using GPT, and we tried fine tune the Metas one, but it just not work as good as GPT.
Gotcha. You said you tried to use the Meta one.
Yeah.
Yeah. Cool.
And like the fine tuning, it did not really have some like the fine tuning with the local version did not exceed the ability of GPT. That's why we're still using it.
Next.
Okay, yeah. If anyone else have a questions, you can ask right now or raise your hand. If not, we can proceed to the final part of this presentation.
I
Where
see another question in
Yeah.
the channel.
Yeah, super.
So about automatic vulnerability detectors. Yeah. So okay. So this is a good question. So it uses the bug. Oh, so bug is like the Foundry invariant or Inchinda invariant you write specifically for your project. So sometimes, let's say if you have a very complicated project and some small restrictions may not result in a very huge impaction. Let's say get your funds got stealed. These invariants must be written by yourself. So you use a bug in the example of our doc, or you can just use the ones you written before in Foundry or in Jinda. But for those, let's say if you're a ERC20, no matter how like complicated it got, if the token can be, say, drained by someone, even the bug is small, you don't need to like write the invariant after some bug is triggered, and eventually the oracle will like get the error. And maybe let's use a Uniswap v2 example. So if some token is flawed, and maybe you don't need to write your own invariant, but eventually the pool will be drained or imbalanced. So that's the generic detectors or oracles we call it, and also that's I think in Chinda also have support they support a lot of bug detectors, and also that's basically the same thing. Yeah. Did that answer your question? Zach Koba?
I don't think he has mic powers.
Yeah,
Okay.
I think, yeah.
Okay, let me move on. There are still a few questions I need to answer.
Yeah, for sure.
Once you get good at fuzzing, what's the meta for fuzzing? What do you mean by that?
So when you play a video game, you can go and play the video game and learn the rules and, play. But when you get to the expert level, there's a level of knowledge and play and strategy that is meta to the actual rules. And that's what I
Okay.
mean by meta. And so it's like what you showed us is, an intro. But I'm wondering for you day to day, like what are the problems? What's the frontier? Like,
Okay. So I think when you get good at fuzzing, or when you get to look into fuzzing, what you do is to understand how the program executes, whether a fuzzing can solve the problem or not. For example, if the example I mentioned in the talk about message sender thing, the fuzzing will never reach that. So you have to understand that. I guess that's the thing. It's a little bit like programming. When you learn programming, you get to know what program can whether program can do this. But if you do not, you might think it's just a mystery black box that does everything or does not everything. Yeah, that's the I think that's my opinion.
that would be such a good resource for you to write down what doesn't work, because that definitely does not exist. At least in the crypto world. I'm sure it exists in the academic world.
What do you mean? Sorry.
If Fuzzland were to write here are where you don't want to try fuzzing.
Oh, yeah,
Have
I
it be
see.
like
Yeah,
very
yeah,
particular.
definitely.
Because that knowledge is very useful and doesn't exist right now, as far as I know. They're all like positive documentation, you know? This is more negative in the sense of do not do this, which
You're
is
right.
still very useful.
Should work on one. Okay, let me move on. How it could find functions in real code arena projects? Yeah, I think for code arena projects, you need to convert the invariants into or maybe sometimes it has a lot of Foundry invariants. We currently support some level of Foundry invariant conversion. You should look into that. But I did not work on that. I'm not sure if the doc is updated, but we have Foundry support. And also, have you all tried to use on-chain transaction for a particular protocol? I think fine-tuning the fuzzer, it's like a trade-off. What we are building is a generic fuzzer. Definitely, like the specific goal-specific fuzzers works better than generic fuzzers. Like it's also like in Web2 space. Like if you have a PDF reader, what's the best fuzzer is that you define every field for the fuzzer, so it can mutate more smartly, so that it can execute more quickly or reaches more branches. Yeah, but I think, yeah, that's my opinion.
That's interesting because I would expect, if you go 2 times deeper for whatever, I'm not sure what metric we're using, but you make it 2 times more specific, you would find a much larger, you would increase your probability of finding a really damaging vulnerability by way more than 2x.
Yeah,
And
that's
that trade-off would be worth it, but it sounds like that's not the business strategy or company strategy. So
yeah. So if we are, I think it's we offer this tools for you to like write those invariants, and those invariants are ready. I guess it can maybe, yeah. Fine tuning is definitely a direction of the fuzzer, but it's just not there yet. But what we did before, one feature we had before is that we analyzed all the previous hacking contracts, and we sort of like fine tune the fuzzer to like we give it the probability to use the distribution like of the function calls of the hacking contracts, and it helped us like find a little bit more than before. Yeah, but yeah, thanks for that. Fine tuning is definitely a better strategy.
Cool. I think we have one more speaker that wants to drop on a scene if you have time.
Yeah.
Sergio, you can just raise your hand and I'll give you a spot.
I think he might not be able to raise the hand.
Okay. Let me ask. Oh, yeah, here it is.
Okay.
Yeah.
Hello. Hi.
Hi.
I would like to ask about your automatic vulnerability detector. Sign it operate in a completely different way compared to other tools. For example, it used the keyword bug applies manually in the contract to attempt to break an invariant in a specific part of the code. And I'm curious to understand how it works internally, as it seems like a very interesting and innovative approach to testing.
I see. So this is like similar to the Inchinda or Foundry. I'm not sure about Foundry, but Inchinda does this as well. So a bug is just a event. So when you reaches a bug, it will send the event, or on the EVM layer, it will call log function log instructions. So the state will log this And if the type of the log is our predefined ones, you may find that in the middlewares or the oracles in our source code, it will like throw the bug.
Okay, very interesting. I am curious about how it could function in real projects. So far, I have conducted various tests with your tool, allowing Blaso, using
Yeah,
it on contract without constructor or on contract that inherit from others.
yes, we're still working on that. We're actually we made our like for our I'm not sure if they updated it yet, but for Blaze, for each of us, we're transitioning to off-chain fuzzing onto on-chain fuzzing, meaning that we will deploy all the contracts on a Envo chain, and we get everything from there. So that yeah, I think we are working on that so that you can just start an Envo chain and deploy the contract using the protocols deploy script onto a local chain and then fuzz with it. So that will be more convenient. But yes, sorry, it's still like work in progress thing.
Cool. Yeah, let's proceed to the final part where I ask two questions basically. It's like visionary one. What do you think about Rust in Common? Because I know that you used a lot for building your tool. And what do you think about the future of Web3 security tooling and how it will evolve through the time for the next 2 or 3 years?
Okay, so our company is founded this year, and I joined officially in September, which means I have a really good prediction of the Web3 space. But yeah, I think for tooling part, I think we should borrow more experience from the Web2 space because it already had a like complex or mature solution. Fuzzing is one of the biggest, and also yes. So I think yeah, that's my opinion. So we have to borrow experiences from the matured ones, and definitely, I guess more. I'm seeing a lot of cool tools recently. For example, when I went to Turkey last month, I get to know like Satora like more deeply, and also Helmut Prover, and I'm really excited that people are realizing that we are lacking of good tools and we are building good tools.
Cool, yeah. And just the question about Rust, because you didn't answer that broadly. Maybe you can tell something more, because we have kind of a focus on Rust in our community, so it would be great if you can collaborate or elaborate on that.
You mean Rust security or Rust development?
Yeah, I mean Rust development, tooling development. What do you think about Rust, and also Rust in Common in Web3? What do you think
Okay.
about that?
Yeah, I learned Rust for less than a year, and I have to say Rust is like it's great. Like starting it is a little bit painful, but it really helped us eliminate a lot of unnecessary debugging processes. And one suggestion as a well, I'm not a Rust beginner anymore, but one suggestion from me is that you should use Copilot to help you to write Rust. And once you saw those completions more, you're comfortable writing your own Rust code. And also, you should try Clippy. Clippy is it's a tool for you to like. It's a linter, it's a static analyzer. Yeah, that's my two opinions. Yeah, and keep using Rust. Rust is really good.
Okay, great. I just want to say thank you for your presentation, for your time, for your knowledge that you shared today with us, and yeah, just thanks everyone who joined us, and thanks everyone who asked question. We'll proceed on more workshops next week, and just stay tuned. And yeah, thanks everybody.